Hello everyone, and welcome to my talk on single particle communication through correlated noise. I'm Hlér Kristjánsson, and this is joint work with Mao Wunshi and Giulio Chiribella. This talk is going to be based on our recent archive preprint, which you can see here. So let's start with a simple communication scenario. Alice wants to communicate to Bob by encoding a message in the internal degree of freedom of some particle, for example, polarization of a photon, and send it through a noisy communication channel to Bob. Now, in many realistic communication scenarios, for example in optical fibers, the noise occurring on successive uses of the same communication channel is in general correlated. So for example, if Alice sends one particle at time t0 and another one at time t1, then the specific choice of errors occurring on the two particles will be correlated, as represented by the yellow regions in the figure. Now, the field of communication through correlated channels has become well established and initiated by Machiavello and Palma, where usually information is encoded over multiple particles, each sent at different time steps, and then some knowledge of the correlations occurring between the time steps is used to do error correction at the end. However, each use of a single particle can also be thought of as a resource. So a natural question arises whether we can use or probe the correlations between successive uses of a communication channel using only a single particle. Now, clearly this is not possible classically, because a classical particle can only be sent at a definite moment in time. However, a quantum particle can be sent at a superposition of two separate times. For example, by initializing the particle through an interferometer with a time delay on one path. So in this work we show that a single particle transmitted at a superposition of two times can indeed probe the correlations between noise at different time steps in a correlated communication channel, and this enables the possibility of error correction using only a single quantum particle. In the rest of this talk, we'll begin by looking at the mathematical framework required for this formalism, then discuss the communication advantages, and finally the wider implications. So let's begin by describing correlated quantum channels. So in this talk, we are going to focus on two-step random unitary channels. That is, random unitary channels with two time steps, where in the first time step, we have some random choice of unitary representing different kinds of noisy processes that are occurring, um, and the second time step, another set of random unitaries will occur, un, and the two are correlated by some joint probability distribution p of mn. Now, the unitaries could, for example, be the Paulis. Now, we're going to describe transmission at a superposition of times through such a channel as follows. So, when we do send the particle, so at the time when we do send the particle, then we model the communication channel as acting on the internal degree of freedom of the particle, for example, the polarization of the photon. But when the particle is not sent, so at the times when it isn't sent, then we model the communication channel as acting on the vacuum state, which is orthogonal to the internal degrees of freedom we are considering. We moreover assume that the evolution conserves the total particle number, so the communication channels we consider do not destroy or create particles. Now in this case, each random unitary from the previous equation will take the following form. equals Vm, some unitary on the internal degree of freedom, e.g. polarization, plus the projector onto the vacuum sector with some phase factor e to the I phi m between the one particle and the vacuum sectors. Now this phase factor, or vacuum phase as we will call it here, will turn out to be crucial for the communication advantages, as we will see later. Now, we are going to control the time of transmission by a quantum degree of freedom. And this can be, for example, the time bin or the spatial mode of the same photon that is being sent as the information carrier. So we take this quantum degree of freedom to be a control qubit, such that when it is in state 0, we send the message, i.e. the internal degree of freedom, through the first application of the channel and the vacuum through the second application. And when the control qubit is in state 1, we have the vacuum going through in the first time step and the particle, the message, in the second time step. So now we can initialize the control qubit in the plus state, in the superposition state plus, so that we really have a superposition of the particle going through at time t0 and time t1. Now mathematically, we find that in this case, the joint evolution of the message rho and the control state initialized in plus is as follows. So we get a new random unitary channel consisting of the original random unitaries Vm and Vn, or sort of a direct sum of the two, but with the additional phase factors phi n and phi m. So as an example, let's consider a random Pauli channel where the unitaries V0, V1, V2, and V3 are just the simple Paulis we all know, I, X, Y, and Z. And as a kind of extreme case, let's consider really the worst possible transmission line when used at a single time step. So really now let's consider the transmission line, for example this one here, really to be such that if we are only using it once, then it is completely depolarizing on the internal degree of freedom. So let's say that Alice is sending a message rho to Bob with the control, initialized either in the state 0 or the state 1, i.e. the particle is sent at a definite moment of time. Then we just get back the same state of the control, and the message is going to be in the maximally mixed state. So this is really just a completely depolarizing channel, so that when used at a definite moment in time. So now let's consider some additional specifications of this communication channel in terms of the correlations between the different time steps. So let's consider correlations such that the choice of unitaries between time steps is permuted. So mathematically, this is described by a probability distribution P of Mn equals a quarter Kronecker delta M sigma of n, where sigma is a permutation of the set 0, 1, 2, 3. Now remember that we're using 0, 1, 2, 3 to count the Paulis I, X, Y, and Z. Now in this case, the effective channel from Alice to Bob is given by C effective of rho, where rho is the message or the input state that is encoded in the internal degree of freedom. And this is given by identity over 2 plus some factor called G of rho, tensor the plus state on the control, plus identity over 2 minus G of rho over 2, tensor some the minus state on the control. Now, G of rho is given by some sum over the off-diagonal elements Vm and V of sigma of M dagger acting on the initial state rho. And in general, it has some non-trivial dependence on this initial state rho, so that communication can potentially be possible through this effective channel. Now note that the G also depends, crucially, on these vacuum phases phi of M. Now, there is a strong dependence on the type of correlations we have. In this case, the permutation in the choice of unitaries. So let's start by considering the identity permutation, where sigma of M is just equals M, i.e. if you have an X noise in the first instance and you get again an X noise in the second instance, etc. Well, in that case, G of rho is equal to identity over 2, no dependence on the initial state, so no communication possible. But for example, for the permutation sigma, which permutes I and X and Y and Z in the two uses of the channel, with choices of vacuum phases, let's say phi 1 minus phi 0 equals 0, but phi 3 minus phi 2 equals pi over 2, so non-trivial differences in the vacuum phases, we get that this G object, acting on the message initialized in the plus-minus state, gives us back identity over 2, or plus-minus identity over 2. And this implies that the effective channel C effective, acting on plus-minus state on the message, gives us back the plus or minus state in the state of the control. So perfect communication of one bit is possible via measurement of the control on the Fourier basis. So what we've done here is we've taken a transmission line that acts as a completely noisy channel at each time step and converted it into a perfect transmission line from Alice to Bob by sending only a single quantum particle, albeit in a superposition of times. Now, in the example we just considered, we picked specific cases of the vacuum phases, but more generally, we can consider a numerical analysis over all possible vacuum phases, which we did, and we see that in the case of the permutation of I and X and Y and Z, as we considered before, we get a very interesting picture where there's really a very non-trivial dependence on these phases, where the whole level information, which is a lower bound of the classical capacity, ranges everywhere from 0 all the way to 1, depending on the choice of these phases. Now, we can also consider the opposite extreme. So previously we really had perfect correlations between the noise, so some permutations of the noisy processes, but we can also say that they are completely uncorrelated. So the noise at time t0 is uncorrelated with t1. And in that case, we can still get some non-zero communication, classical communication capacity, when even if each use of the channel in isolation is a completely depolarizing channel. But we find, as with the numerical simulation you can see here, that the maximum whole level information is 0.16. So this is considerably less than the unit capacity we found for the correlated case. So you can read more about the kind of superposition of uncorrelated channels, which is a field in itself, in the two papers cited here at the bottom. Now, just before the end of this talk, I would also like to point out a kind of separate discussion that correlated channels can be useful for. So the use of, or the correlated quantum channels can also be used to simulate the use of ordinary quantum channels in a superposition of alternative causal orders. Now, if you're interested in indefinite causal order and how these kind of correlated channels might be able to shed some light on the discussion of communication through superpositions of orders, then please see our full paper on the archive. And you might also be interested in my other talk here at AQIS'20 Resource Theories of Communication, which is also a recent NJP paper. So this brings us to the end of this talk. So we have shown that a single quantum particle can probe the correlations between different uses of a transmission line. Coherently controlling the time of transmission can boost the communication rate beyond what is possible when the transmission line is a classical variable. And moreover, our framework enables quantum effects to be fully utilized. So now, not only are the information carriers quantum states, but the time of transmission is also. This can be applied to various realistic communication scenarios where, in general, the noise is correlated between different uses. And an experimental proof of principle is currently underway at Imperial College London, where we're also probing the vacuum phases in practice and experiment, which we hope to be able to present to you next year. And with that, I would like to thank you for your attention.